multiply your table answer by 95% or 90%. A contractor will work a problem when you're doing any of these problems out of walkers. A Sheepsfoot Roller is a typical example of the problems out of walkers. Is they give you a chart answer. Then once you find the chart answer, then you modify it to meet your site requirement. So here's an example of this a Sheepsfoot Roller problem. Contractors compacting 10,000 cubic yards of loam. Loam is sand, in 6-inch lifts. She is using a 10-foot wide Sheepsfoot roller moving at 2.5 miles an hour. There will be 6 passes at 90% efficiency and 5% loss in time due to maneuvering. The time required to compact the loam is how many hours? So your example, you've got 10,000 cubic yards, 6-inch lifts, 90% compaction, 6 passes, a turning factor of 0.95 or 5% loss of efficiency. So we go to the walkers and solve the standard problem. 6 passes in loam is 367 cubic yards an hour. 367 times 0.5 because we're using 6-inch lifts, times 2 because we have a 10-foot wide roller instead of a 5-foot wide roller, times 0.95 because we've got a 5% maneuvering loss, gives us 348 cubic yards per hour that we're going to be compressing. So 10,000 cubic yards divided by 348 yards an hour means it's going to take 28.68 hours to complete this job. When you solve all these problems out of walkers, it's basically like the Sheepsfoot Roller problem. Okay, the next problem is dragline yardage problems. This problem is a good deal like the Sheepsfoot Roller. You have a number of variables and you have a chart that has a standard answer or a perfect world answer. The quantities in the tables represent cubic yards moved from the bank rather than cubic yards in the hauling unit. There's a big difference between these two. This is because of swell, which will increase volume by 10% to 30%. That's out of Chapter 2 of walkers. The optimum depth of cut for various sizes of shovels may be defined as that depth which produces the greatest output and at which the dipper comes up with a full load. Okay, this is all right out of walkers. Number 3, the dragline is working a full 60-minute hour with no delays for adjustment, lubrication, or operator needs. The full dipper is swung through an arc of 90 degrees, like this, before dumping. This is important because the swing of either lesser number or greater number of degrees than 90 degrees will either save or consume time and affect output capacity. The shorter the swing, the more yardage the shovel can dig. The hauling units can hold a minimum of 1 dipper or shovel capacity, and there are enough trucks or train cars to take away the material the shovel can dig. So the chart assumes that there's no constraint in being able to take off everything that the shovel can dig. Here's a dragline yardage problem. What is the production capacity of a 1 cubic yard bucket working in moist loam? Moist loam again is sand. That's what mostly you're going to get on the contractor's exam in Florida, is the questions asking you about moist loam, because that's sand. All right, so here's the problem again. What is the production capacity of a 1 cubic yard bucket working in moist loam for 1 8-hour shift? Now you need to note the difference between the different dragline shovels. There's the hourly shovel output in cubic yards, and then there's the hourly short boom dragline output in cubic yards. Make sure you use the proper chart when you're solving the problem. If you use the wrong problem on the exam, you're going to get it wrong. So you've got to read these problems carefully and match up the question they're asking to the chart and walkers. So we have 205 cubic yards per hour times 8 hours equals 1,640 cubic yards per 8-hour shift. Now, if they were asking us for the short boom dragline output, that would have been 160 cubic yards per hour times your 8 hours would give you 1,280 cubic yards per 8-hour shift. So you got to use the right chart. Dragline yardage problem. Note that the normal or optimal case occurs in the column where the depth of cut, the percentage of optimum, is 100 feet, and the angle is 90 degrees. And so right about in the middle of this chart, you're going to have your 100% category. If you go to the left, right, up, or down, you're going to be adding or subtracting capacity. You can use this table to calculate other options, such as 100% depth of cut and a 75-degree swing would give you 107% efficiency over a 90-degree swing. So if you, instead of going a 90-degree swing like this, if you can go 75%, you're going to be picking up 7% efficiency. So if you can go faster, if you can move it less, you're going to be able to work faster, save money. There are other options the exam testers might use, such as a 90-degree angle and an 80% optimum capacity. Here's another question. What is the production capacity of a 1 cubic yard bucket working in moist loam for one 8-hour shift with a 75-degree angle of swing and 40-foot optimum depth of cut? Okay, so let's do it out of Table 2, hourly shovel output in cubic yards. Again, we have 205 cubic yards per hour times 8 hours gives us 1,640 cubic yards per 8-hour shift. We're going to multiply that by 105% because we pick up 5% efficiency by having a shorter swing, okay, by only going through a 75-degree arc, and by using a 40-degree optimum depth of cut. So we're going to pick up 17, so the 75-degree gives us a 5% advantage, so we're at 1722. The 40-degree optimum is at 97%, and so it's cutting down your capacity back down to 1,670 cubic yards per 8-hour shift. If we were using the short boom dragline to solve the same problem, again, 160 cubic yards per hour times your 8 hours gives you 1,280 cubic yards per 8-hour shift, times your 105%, you're picking up your 5% for a shorter angle of swing, and then you're losing 3% because of your optimum depth of cut, and so you'd be at 1,304 cubic yards per 8-hour shift. The good news is that on the exam they'll probably give you a problem right out of the chart, that they won't require you to calculate an angle of swing of 75 or something other than 90. Calculating diesel fuel consumption. You take the bulk horsepower times your factor times your pounds of fuel per horsepower per hour, and this is the basis for your formula. You have weight of the fuel per gallon. Bulk horsepower equals your brake horsepower or rated horsepower of the engine. Your factor depends on the load or torque of the engine, and it's going to be either 50 or 60%. Diesel equals 0.5 pounds times your brake horsepower. That's just a given calculation. And diesel fuel weighs 7.3 pounds per gallon. Your diesel fuel problem will solve the problem of a diesel skid loader with a 75 horsepower diesel and an 18-gallon fuel tank. 75 bulk horsepower times 0.50 times 0.50 divided by 7.3 pounds per gallon equals 2.57 gallons per horsepower. Okay, so 2.57 gallons per horsepower times 1.15. You have to add 15% for fuel cost and lubricating, so you may as well add it in at this point. So now your consumption is going to be about 2.956 gallons per hour with your lubricating oil and fuel costs added. Now, that's the hard way to do it. That's right out of Walker's. You got the long way, the formula from Walker's. Now, the short way is you take the calculation of 0.040 times your bulk horsepower of your machine, which in this case is 75 horsepower, and you multiply 0.040 times 75. That gives you 3 gallons an hour. If you remember the long way calculation, we ended up with 2.956 gallons an hour. Takes a lot longer and you got to figure it out. This one you don't have to remember putting in 15% for lubrication costs. It's simply 0.040 times your bulk horsepower gives you your consumption per hour. Hauling calculations. The next calculation we do are hauling calculations. These are out of our next book. Principles and practices of commercial construction. Many factors affect the choice of what machine to use. The following are major considerations when in hauling calculations. And these are questions they like to ask you on the exam. The type of material to be excavated and hauled, the site conditions, the distance of the haul, the time allowed for job completion, and the contract price. Hauling calculation formula. The formula is P equals production, cubic yards per hour, and that's the end bank. E equals your machine efficiency, minutes per hour. I equals your shrinkage factor for loose material. H equals your heaped capacity of the machine in cubic yard. And C equals the cycle time of your machine. Okay, we'll go through each one of those. I, calculating for I, materials can increase in volume by as much as 50%. To allow for this increase in volume, the shrinkage factor, I, is applied to the heaped capacity, H, of the earth mover to reduce the load to the end bank condition. Okay? So end bank machine capacity equals H, or heaped capacity, times I, or the shrinkage factor. Okay? Your formula for calculating shrinkage is worked out for you, and the principles and practices of commercial construction, we're going to go through the formula. I equals 1 over, or 1 divided by 1 plus your swell factor divided by 100. Okay, 100%. Okay. I is solved for you in the book, in Principles and Practices of Commercial Construction. I is solved for you for 25% swell and 50% swell. So you don't have to work out I. On the exam, I in this problem is already worked out. It's in the book. All you do is look it up. Calculating E, or machine efficiency, is included in the calculation as an average piece of machinery is between 75 to 80% efficient. This efficiency percentage is assigned to the machine. Some examples of machine efficiencies are a crawler tractor works a typical 50-minute hour. A rubber-tired hauling unit works an average of 45 minutes an hour. Large rubber-tired loaders work a 45-minute hour, and your small rubber-tired loaders typically work 50-minute hours, or they have 83% efficiency. So that's what you need to know. 50-minute work hour is 83% efficiency. A 45-minute work hour is 75% efficiency. Calculating C, or cycle time, of a piece of equipment is based on the time required to obtain its load, move to the dumping point, and return to the loading point. Total cycle time is a combination of cycle travel time plus cycle fixed time. And typically in the test problems, they'll give you this. They'll say your cycle time is 2 minutes or 5 minutes or 10 minutes, but it'll be a given. But for out of the book, for the sake of argument, your cycle time is calculated as your distance divided by your speed times 88. And 88 is a constant, which, so it's a distance divided by speed times 88, which is your constant. That's calculating C. Calculating H, according to the Principles and Practices of Commercial Construction, page 74, the heaped capacity of a 1.5 yard bucket is 2 yards. So your heaped capacity is the amount the bucket will hold if it's heaped. And so a 1.5 yard bucket is going to hold 2 yards. All right, so here's an example problem. We calculate the production for a crawler-mounted power shovel working in well-blasted rock with the 1.5 yard bucket. The machine has an efficiency of 50-minute hour and a cycle time of 3 minutes. The percentage increase in volume for rock is 50%. This is worked out for you on page 72 and 73 of Principles and Practices of Commercial Construction. You don't have to calculate I. Don't spend 15 minutes figuring out about I. It's already done. So I equals 1 divided by 1 plus 50 divided by 100 equals 0.67. As I said, 0.67, I is already figured out. Now let's go through it. P is what we're trying to solve. E, efficiency is, we're told, a 50-minute hour, so that's 0.83% efficiency. I told you, is already given for rock and for clay, and in this case it's 0.67. Your heaped capacity, we're using a 1.5 yard bucket. Your heaped capacity is 2 yards, and your cycle time is 3 minutes. Right, so we know now we have all the pieces of the problem. Now we solve for P. 0.83 times 0.67 times 2 divided by 3 gives us 67 cubic yards divided by 3 minute cycle time. Means you're doing about 22.24 cubic yards an hour with that machine. That's the end.